Here's another example of finding the volume of a solid of revolution using the disk and washer method. Find the volume of the solid generated by rotating the region bounded by y equals 2 square root of x, y equals square root of x, and x equals 7 about the x-axis. As usual, our first step will be to graph the region involved. Let's start by placing the line x equals 7 on our graph so that we have a reference for roughly how big our graph should be. Let's put it right about here. This is a vertical line in this position. X equals 7. Now we can graph y equals the square root of x. As we know, that is the top half of a parabola that opens sideways to the right on the x-axis. It will go through the origin. In fact, the vertex is at the origin. And it will go slightly vertical, and it will curve over like this. It's concave down, but has a positive slope. Y equals the square root of x. For y equals 2 root x, that's just a transformed version of the graph we just drew. It's been stretched upward by a factor of 2, so it still starts at the origin, but it's going to go up a little higher and curve over like this. And I'll extend my line here to reflect that. This is y equals 2 root x. Now we can fill in the region that will get rotated about the axis. It's this region right in here. The region that's in between the two curves and the line. And right away, while we're at it, while we're looking at our graph, let's note what the bounds are on x. The bounds are clearly going from 0 at the left to 7 at the right. So we'll save that away for future reference. As in the last example, we want to rotate this region about the x-axis to get a solid, a three-dimensional figure. Here's our x-axis, our axis of rotation. You can always draw a little circular arrow to show that you're rotating about that axis. And I will emphasize my axis here in green. And let's try and draw a rough idea of what this three-dimensional object looks like. It can help to reflect your region over the axis first. It's going to end up right down here. In fact, the other halves of those two parabolas will show up right down here. Here is that region. Okay. And I can shade this portion as well. Now let's see what our three-dimensional object looks like if we just twirl this object around the x-axis to make something that's 3D. The center is going to make a shape that is called a paraboloid that has circular cross-sections, but the outer parabola will also make a wider paraboloid. So the rightmost face of this object is not just a disk this time, it's a disk with a hole in the middle. And subsequent slices of this thing will also have holes in the middle. As usual, I like to try to describe my object in very comfortable and familiar terms so that I have a better sense of what it looks like three-dimensionally. I would call this thing sort of a bowl or a flower pot maybe, with a hole in the center. It's got a hollow interior, but it's thicker near the outer edge than it is at the center. Now let's look at what happens if we slice this object up into slices that go perpendicular to the axis of rotation. As usual, we'll get some slices that are roughly circular, but what do they look like exactly? Again, we can work this out by drawing a typical Riemann rectangle inside the region that we originally started with. Because our variable is x and y is a function of x, we'll make our rectangle very thin and vertical, like we usually do. Here's our typical Riemann rectangle. What happens if we rotate this around the x-axis? Well, it's going to end up down here. And the shape that it will trace out is not exactly a disk. Instead, it's a disk with a hole in the middle, a ring. It still has some thickness. Some thickness here. In fact, what we call this kind of shape is a washer. If you've not seen a washer before, it's a little piece of hardware you can find at the hardware store, a little metal ring with some thickness that has a hole in the middle. So we call it a washer. So here is the xth washer, disk with a hole in the middle. Looks like this. Still has some small amount of thickness, but there we go. As usual, we'll need to figure out the dimensions of this washer and eventually the volume. So to work this out, well, one part's easy. The thickness of that washer is still dx, the same as it was last time, because it's the same as the width of the rectangle. We also need to find out our radius. In fact, there are two radii. There's the large radius from the center to the outer edge. There's also the small radius, little r, from the center to the inner edge. We can see what those look like on our graph. Here is our large radius, big R, and here is our small radius, little r. Okay. What are these values? Well, our big R is the distance from the center of that washer to the outer edge. It's going to be the y-coordinate of the higher of the two curves. In fact, it's the distance from that curve to the x-axis, which is just going to be 2 square root of x. Our small radius is the distance from the center to the lower of the two curves. That is the square root of x. So we have our two radii. We still need to find the volume of this washer. The volume is always going to be the area of that surface, that ring, that circle with a hole in the middle, times the thickness, which is dx. So we need to find the area of the face. Well, that's going to be the area of the big circle minus the area of the small circle. So that's pi big R squared minus pi little r squared. So in this case, that's going to be pi times 2 square root of x, all in parentheses, squared, minus pi times our little r, which is root x squared. Now, what we need is the volume of that washer. Well, that's just the area of that face of the washer times its thickness, which is going to be pi times big R squared minus pi times little r squared times dx. Now we're ready to set up our integral to find the volume of the entire solid of revolution. We know the volume of each individual washer. It's pi times the big radius squared minus pi times the little radius squared, that whole thing times dx. We just need to fill in our big and little radii, and in the case of the particular functions that describe our region, the big radius is 2 root x and the small radius is root x. So we can fill those in. Our volume of our solid is the integral of this expression above, pi big R squared minus pi little r squared, whole thing times dx. In fact, we like to pull that pi out again. You can factor pi out of all of the terms of the integrand, and therefore you can factor it entirely out of the integral and say it's pi times the integral of big R squared minus little r squared in parentheses times dx. And of course, that'll go from some bound to some other bound. This is the general formula for the volume of a solid of revolution using the washer method. And the only difference between the disk method and the washer method is that for the washer method, your disk has a hole in the middle. And therefore, you'll subtract the area of the smaller circle in that disk. So for our specific problem that we're looking for, we'll just fill in our big and little r's and our bounds. Our volume is pi times the integral from 0 to 7, we worked out already, of our big R squared, that's 2 root x squared, minus our little r squared, which is root x squared, whole thing times dx. That is the integral that we need to solve to find the volume of this solid. So let's solve this integral. Our volume is going to equal, again, we want to do some algebra and simplify our integrand before we do anything else. We've got pi times the integral from 0 to 7 of 2 root x squared. We're going to square the 2, that gives us 4. Root x squared, well, the square root of x squared is just x. Minus, well, root x squared again, that's just x times dx. Gosh, this is just an easy integral right here. That equals pi times the integral from 0 to 7 of, well, 4x minus x is 3x dx. So very simple. We've got pi times 3x squared over 2, going from 0 to 7. Bring this around here. This equals, well, we'll just fill in our bounds now. We're going to have, let's pull that coefficient out front, 3 pi over 2 x squared, that's going to be 7 squared minus 3 pi over 2 times 0 squared. That part again goes to 0. And 7 squared is 49. 49 times 3 is 147. So 147 pi over 2. Again, we'd like an exact answer here rather than a decimal approximation. So this is the best answer we can write.